next we've got our very own Ron Yurko. A little quick background on Ron here. He's currently a statistics PhD student at CMU once again. Ron also did his undergraduate in statistics here at Carnegie Mellon. He graduated in 2015. He served as a baseball operations data and analytics intern with Pittsburgh Pirates in 2014. And he later on worked as a quantitative analyst in the financial services industry. And most notably, he was my freshman year stats team. So, without further ado, here's Ron Yurko.
Alright, to get started, the current state of football analytics is not easily reproduced. It's largely driven by companies with proprietary data, charting information, manually collected, and this is a problem. It's a problem because football doesn't have a community, the football analytics community, such that we see in baseball, hockey, basketball. We get insight from the public, we have fan graphs for baseball. It's a lot of community research. It leads to a lot of insight into the game. And likewise, teams end up plucking these people from the public and become better. It's smarter sports. So an answer to this was Max Horowitz created the NFL Scraper package in R. And this allows you to easily access play-by-play data going back to 2009, download it to GitHub, install the package, and you can perform your own data analysis and share your code so we can have reproducible research. What we've actually seen is various blogs, websites have been using the package. I started developing it more with Max this past year, more advanced metrics, and we've seen Seattle Seahawks blogs using it, and it's grown in popularity. So recently, Liz Bloom of the Post-Gazette wrote an article on NFL Scraper, her state of football analytics. And being young and naive, I made a terrible mistake. I read the comments. Stats geeks like these that are ruining sports. You know, you're not going to please everybody, especially Pittsburgh sports fans. Now another comment. Stats don't work as well in football as compared to other sports such as baseball. You can't statistically evaluate a running back without evaluating his offensive line. And they go on about quarterbacks and receivers, and of course end with a statement, the only thing that matters is the W, the win. This is actually a great comment. You're recognizing the fact that football is indeed a team sport. In every play, we have a lot of moving pieces. So we can't just say, okay, this running back gained 10 yards, or Big Ben for a 30-yard touchdown to Le'Veon Bell. We got to divide the credit up there amongst the players. It's a lot more difficult than in baseball, these independent states between pitcher and batter. Football has a lot more pieces. So with NFL Scraper, we decided to introduce our NFL WAR, a reproducible framework for offensive player framework for wins above replacement in football. So the whole goal of NFL WAR is we're going to properly evaluate every play. We're going to come up with a way of getting an individual contribution in every play. We're going to evaluate this relative to replacement level. This is important because for a team's perspective, average is still technically better than roughly 30 to 40% of the league. If I'm someone on a team in the front office, I really want to know how much better is this person than someone I can just grab off the practice squad. Then we're going to convert this to a win scale, because ultimately then from a team's perspective, in terms of managing our payroll, looking at our salary, and what players we want to identify, we got to think about how it relates to wins, because wins translate to dollars. This is important for a team. And the final thing is we want to estimate this uncertainty for. Naturally, it's an estimate of their talent. So we're going to see a possible range of values given their performance. And we can apply this framework going back to our data since 2009. To start then, in terms of how we value plays, Brian Burke talked about this at the beginning. We have two main ideas, expected points and win probability. So expected points, given this current state, given it's 3rd and 1 on our 20-yard line, how many points are we expected to score, given how other teams have done historically? And then the same thing with win probability. How likely are we to win the game, given this current situation? Now today I'm just going to focus on the expected points, but this NFL WAR framework we're introducing, you can actually apply win probability in this sense. Now there's several ways to do the expected points modeling. But really if you think about it, for every play we're just looking at the next score. So there's only 7 real outcomes if we're ignoring point after attempts. For the team with possession, we can have a touchdown, field goal, or safety, and then we can have our opponent doing the same thing against us, or no score being the next event. Now, I placed this So along the y-axis is actually showing those point values, all right? And then the x-axis is the number of plays with that type of event, is the next score. And clearly you can see it's an offensive-driven league. But for the statisticians in the room, one of the things that's most common is people just take a linear regression approach. Now, if you look at this vertical spacing, this is actually kind of a problem. So for the stats students at CMU, one of the first things you do, you fit a linear regression model, you're checking your residual diagnostics. So for a linear regression model, we just want to see a random scattering of points. That's not the case here. It's a disaster with the expected points model. This is actually then a classification problem. So what we're using is a multinomial logistic regression model. So for each of these events, for the touchdown, the field goal, safety, and then the opposing ones as well, and no score, we're actually predicting the probability for each of these occurring for every play. And then to just get the expected points for a play, we're taking that probability, multiplying it by our associated point value, and then we're adding it up across. And then we get our expected points. Now to get then to a value of a play, we're going to look at the expected points added. Expected points added is simply just the change, the difference between the end of the play versus the start of the play, the expected points, giving us this actual point value. Now we don't just have to stop there. We have the air yards for every play, for every passing play. So we can actually calculate air EPA. Given how far the ball is thrown in the air, what's the hypothetical expected points added just from the air? And then we can separate that from the yards after catch as well. So we have air EPA, we have the app EPA. Going into this then, we really want to know how much credit does each player deserve. So for instance, Matt Ryan, one of the best QBs in the league last year. Say he throws a touchdown to Julio Jones, 40-yard touchdown. We want to divide that up. If the ball's only thrown 10 yards in the air and then Julio Jones ran for another 30, how much credit is due to each? Do we just split it there? Or do we actually look at maybe there's some contribution because of his accuracy into the yards after catch for Matt Ryan versus then also Julio Jones being able to get open? One player is not solely responsible for a play's expected points added. So how do we actually allocate this? One of the most popular approaches is total QBR, ESPN. It's the whole division of credit modeling, and they're using their proprietary data, and they're getting this idea of how much contribution a quarterback has on every play to develop their rating. But for publicly available data, I only know who's directly involved in the play, who's throwing the ball, who's the target of the pass, who's carrying the ball. And then I also know then which, for rushing plays, where they're running, left, middle, right, as well as in the gap. Now the approach that we decided to take is a multi-level modeling approach. So this is actually growing in popularity recently in terms of then being applied to sports as well. Due to baseball prospectus, they have their deserved run average, and they're using a mixed model approach. The whole idea here is it's a natural approach for when you have group structure in your data. So for instance, on a passing play, I have our passer, I have our quarterback, and I also have receivers. Now they're two separate groups, and they have two separate levels of variation. We have a lot fewer quarterbacks in the league than we have people potentially at receivers. So our spread of talent is much wider for receivers than it is for quarterbacks. And also, this is a natural approach for when you have repeated measures. And in sports, every play is a repeated measure of performance. I know how well Big Ben is throwing when he's throwing to Antonio Brown against the Cleveland Browns versus when he's throwing, well, stop throwing now, to Martavis Bryant against the Baltimore Ravens. So as I said, so this is gory math details here. So the idea is every group is given a model. So in this case, we have our basic linear regression, but then we also have our groups for quarterbacks, receivers. So we have this level of variation, its own variation for quarterbacks versus the ones we have for receivers. And so one of the benefits of taking this approach is we're doing this polling effect. So for players that don't have many attempts, don't have many plays, we're actually just going to put them at the average. So we haven't observed enough. But as players get more and more attempts, and we see how much better, say, Tom Brady is better than average, we're going to keep pushing his effect. We're going to get his value above average. So we're going to take this idea of these varying intercepts, these different groups. And as I said, we actually have this team side gap for rushing. We know what the team is, we know which direction, and then we know whether it's end, guard, or middle. So it's almost sort of like a proxy for O-line. And what we end up doing is we separate the models for the passing and rushing. So for passing, I know the team, I know the quarterback, I know the receiver, and I know the defensive team as well, because we want opposing defense adjustments. Then for rushing, I have the team side gap, the rusher, and the defensive team again. So what we end up coming out of this is for each individual player, we have an IPA. So we named the stat after a beer. Individual points added. And then for each, we also have then a TPA stat for these intercepts for the team groups. And then what we do is that each of these intercepts. I'm just going to click that. So then, because each of these intercepts is actually how well the person or team is relative to that average level, that group average that we're partially pulling towards. And then, so what we can do, we multiply these individual intercept values, the IPA, TPA, by the number of attempts, and we get their respective points above average. So for rushing, we come up with two different models. We're separating rushing attempts for the skill players, the running backs, fullbacks, the tight ends, because these are supposedly designed rushing plays. We're separating this from quarterback rushing, where we don't necessarily know in our data what is designed versus, say, the different scrambles, avoiding sacks. And we're actually including sacks in our rushing model, because we want to get the effect of different quarterbacks that are mitigating the damage from sacks. So for quarterbacks, then, we don't have this team side gap measure. We just replace it with the known team. And this gives us then our IPA rush, as well as then our TPA rush side gap estimates. And so this is what I'm referring to when I'm talking about the variation. So in our multi-level model for the rushing for just running backs and the other skill positions, we can see that the defense, because it's only 32 teams, is much more limited, it's much smaller than the variation we see for the running backs, for the team side gaps as well. And then we see a similar thing for the QB rushing model. Now, what I'm showing here, along the x-axis, we're summing, so each team side gap has this TPA value. So the x-axis is just the sum of those 5 values. Think of that as like this is the pure efficiency of a team's team side gap proxy, their O-line proxy in terms of rushing. The y-axis, I'm taking each of these values and I'm multiplying it by the number of attempts and then summing it together. So then we can view here, we divide into quadrants,